Okay, we're on the second page of the Fall Exam Review Worksheet 2, and let's start off with limit definition of a derivative. Limit definition of derivative is simply, this is merely an expression for finding the derivative or finding the derivative at a point. When we first started talking about derivatives, we first learned the limit definition method. And then once we went through all that process, then we learned, basically after we connected the fact that derivative is basically slope as x approaches 0, then we went to the shortcut method starting with the power rule. So we no longer have to evaluate the derivative using the limit definition, but we still need to know what this represents in the given problem. Okay. So let's look at 4a. Okay, it says find the limit as h approaches 0 for x plus 4, x plus h to the 4th power minus x to the 4th over h. Okay. I think students, when they see this, I think they just want to try and evaluate the limits using limit rules or using limit properties. But the important thing is we need to be able to recognize that this represents something else. Okay? This is representative of finding the derivative of a given function. So if we can figure out what this represents and what this is asking us for us to find, then we can then it'll be a lot easier because we can just figure out what this is representing. Okay. So we're not trying to evaluate the limit, we just have to know what this means. So this is asking for us to find the derivative of a specific function. So the function is going to be x to the 4th. Okay. And once we identify that this function, that this is talking about x to the 4th, and we know that this notation is asking us to find the derivative, then we can just simply go through the derivative method that we know with power rule. So x to the 4th becomes 4x cubed, and so this notation is just asking for us to find the derivative of a given function, so just 4x cubed. Okay, so that's just something that students have to be able to recognize and be able to, in a sense, decipher. Okay. Now if you look at, this is, I meant for this to be part B, that these two problems look very much alike. Okay. The only difference is that instead of the x's have now been replaced with 2. Okay. So this is asking for us to find the derivative function. This is asking for us to find or to evaluate the derivative at a point. Okay. And this is really talking about the same function, talking about the same derivative. We should take the additional step of evaluating this derivative at this given point, and you see that the x's have been replaced with 2. So simply find the derivative at this point. Okay. So again, same function, x to the 4th, same derivative, 4x cubed. We should now need to take the additional step of plugging into your derivative. So replace x with 2, we get 2 cubed is 8, 8 times 4 is 32. Okay, part B. This is again notation for us to find the derivative of a specific function, and the specific function is going to be this square root of x. Okay. So if we know that the function is talking about square root of x, we can evaluate the derivative, which is simply going through power rule, this is x to the 1/2, bring down the 1/2, subtract 1 from the exponent, so 1 over 2 root x. So that's it, just finding the derivative of this function. Just have to know how to decipher that information. Okay. If you compare this problem with part C, you see that the only thing different is that we've replaced x with 9. Now it looks like this x is a little bit different, but technically it's square root of 9, which is 3, so that's why there's a 3 there. So it's the same function. All we're doing is we're taking the additional step of evaluating this derivative at 9. So plug 9 into the derivative function. Plug and square root of 9 becomes 3, so 2 times 3 is 6, so therefore 1/6. Okay, next section, position, velocity, acceleration, and particle motion. So let's look at some problems dealing with that. A particle moves along a horizontal line. Its position is given by x of t for values between 0 and 4. So let's first talk about difference between displacement and distance. So displacement is simply the amount traveled from your initial point to your endpoint. So you're just looking for the distance between your starting and end point without taking into account any change in directions. Okay. So all we're doing is we're finding the position at the starting point. We're finding the position at the ending point, and then just subtracting those two values. So that's all we need to do. So plug 0, plug your starting point 0 into your position function, and that will get you your position. In this case is 27. Plug 4 into the position function, you'll get 35, and then we just subtract these two values to find the displacement. So 35 minus 27 is simply 8. Okay. Now to find the distance, this usually requires more work, because we have to consider that there is a possible direction change somewhere between the starting and end points. Okay, so the way we can determine whether there is a change in direction, we need to first find the velocity function. So we have the position function, we go through power rule, the appropriate derivative rule, in this case is power rule. So negative 2t, negative t squared becomes negative 2t, 6t becomes 6, 27 goes to 0. So we set our derivative equal to 0 to determine where the particle is motionless. So negative 2t plus 6 equals 0, solve for t is equal to 3. And then we put this on a sign line, 0 being our 0 and 4 being our starting and end point, 3 being the critical point. And then we plug values in each interval into the velocity to determine which direction is moving. So between 0 and 3, the object, if I plug in 1, I'm going to get a positive value. If I plug in 3.5, I'm going to get a negative value. So the object is moving to the right, and then it stops, then it goes back in the other direction. So there is a change in direction, so that means we need to identify the position at the endpoint and the critical point, and then determine the distance between the first 2 points, distance between the second and third point, and then we add them together. Okay. So at 0, we know the position is 27. We found that from part A. At 4, position is 35. We found that from part A as well. The new point is 3, where the object is motionless. So plug 3 into the position function, and we're going to get 36. Okay. So the object will start at 27, move forward or move to the right to position 36, and then move backwards to position 35. So then between these 2 points, we find the distance between those two. So 36 minus 27 is simply 9. And then we find the distance between these 2 points, where this object or this particle is going to start moving backwards. So it goes from 36 to 35, and it travels a distance of 1. So he travels 9 in one direction, he travels 1 in the other direction. So total distance will be 10 units. Okay. Part C. At t is equal to 2, the particle speed is increasing or decreasing. Now to determine whether speed is increasing or decreasing, we have to compare the signs of the acceleration and the velocity. So at 2, we first need to find the acceleration function. So we look at the velocity, we find the derivative, negative 2t becomes negative 2. 6 is a constant, goes to 0. So acceleration will always be negative 2. We plug 2 into the velocity, we're going to get negative 2 times 2 plus 6, so that'll give us positive 2. And acceleration at 2 is always negative 2 because there's no variable place. So it always remain at negative 2. So we see velocity is positive, acceleration is negative. So since velocity and acceleration have opposite signs, we know speed is decreasing at t is equal to 2 seconds, or t is equal to 2. Okay, number 6, the position function is given by t cubed minus 6t squared plus 9t. So same steps as number 5. Plug the endpoints into the position function, and to find displacement we just subtract those two values. So 20 minus 0 is simply 20. To find the total distance traveled, we need to find the critical points from velocity. So from a position function we find the derivative, z equal to 0, and we solve for t. Factor out the 3, and we get t minus 3 times t minus 1, so t is 1 and 3. Put them on the sign line. Plug each of these, plug values in each of these intervals into the velocity function. We see that we get positive, negative, and positive. So the object's moving to the right, moves left, and moves right again. So there's a change in direction at 1 and 3. So we need to identify the position at each of these points. So plug all these x values back in, these t values, sorry, back into the original position function. We know 0 and 5 will give us 0 and 20. The ones in the middle are s of 1 and s of 3. So plug 1 into the position function, you get 4. Plug 3 into the position function, you'll get 0. So then just find the distance between each of these points. So between 0 and 4 it's 4, between 4 and 0 is 4, between 0 and 20 is 20. So all these values should be positive. We add them together, we're going to get 28. In part C, when is the particle speeding up and when is it slowing down? So this is a little more work than part C from above, because we need to identify when, not just at a specific time, but for all the time intervals, when the particle is speeding up and when it's slowing down. So we do compare the signs. So for acceleration, it's simply 6t minus 12. Factor out the 6, we get t equals 2. Put them on the sign line, and we test each value. We get negative and positive. Now we're going to put this sign line information from velocity and acceleration onto the same sign line. So both these sign lines put onto the same one, and we can just compare the signs. Okay, you see that between 0 and 1 and between 2 and 3 the signs are opposite, so therefore slowing down. Between 1 and 2 and 3 and 5, same signs, so therefore speeding up. Okay, number 7, this is a calculator question. An object moving along a line has velocity v of t, where t is between 0 and 10. So for what value is the object motionless? So just like before, to find when the object is motionless, we set the velocity equal to 0, but this is not going to be as easy to solve by hand. So we're just simply going to put this in the calculator and see where the graph crosses the x-axis. Okay. So in the calculator, it should look something like this. Okay. Plug in y is equal to x cosine x minus natural log of x, and zoom 6 will get you the graph. It looks like initially the graph may touch the x-axis close to the origin, but once you adjust your window and zoom in, okay, then you're going to see that it's not going to cross the x-axis. It's only going to be at these values. And once you do trace for values close to it, and then you can find left bound, we can make it, okay, and we choose a point that's above the x-axis, and you're going to get 5.1, and then do the same thing for this point, and you're going to get 7.55. So then the x-intercepts will be where the object is motionless, and we see that the object changes, reverses direction, moves left in this interval, moves right, and moves left again. So for part B, we can simply say that this object reverses direction twice, at 5.107 and at 7.55.